Hello, my name's Kate Pattle, and I'm going to be talking today about recent JCMT Pol 2 observations of the two-component magnetic field of M82. So I'd like to thank the organisers very much for giving me the chance to tell you about this work, which I did while I was at NUI Galway, National University of Ireland Galway, although I've recently moved to UCL. My collaborators in this work were Walter Gear, Matt Redman, Matt Smith, and Jane Greaves. So M82, I expect most people know all about it already. M82 is the nearest starburst galaxy to the Milky Way. It's at a distance of about 3.5 megaparsecs. And it's got a central starburst region, which was triggered by its interaction with its neighbour, M81. So M82 is classed as irregular, but it does have a bar, and also it has weak M=1 spiral arms, although they're very much not apparent in the optical imaging. But what it's perhaps most known for is it's got a galactic superwind. This is a wind from the central starburst region that extends about 11 kiloparsecs above and below the galactic plane. You can see it in H1 imaging here in the red, and it's really quite a dramatic feature. So what we wanted to investigate in this study is the magnetic field in this galaxy. How similar is it to the Milky Way? And our tools for doing this was dust emission polarimetry. So emission polarimetry results from the fact that light extincted and emitted by dust grains is partly polarized. And I mean, that's been known about for a very long time now. And emitted light from dust grains is polarized perpendicular to the plane of sky magnetic field direction. That means that the dust grains are preferentially aligned with their minor axis parallel to the magnetic field and their major axis perpendicular. To recover the plane of sky magnetic field direction, we take the polarization angle and rotate it by 90 degrees. All of the vectors that I show throughout this presentation have been rotated by 90 degrees to trace the magnetic field direction. The current leading theory for why this happens is radiative alignment torques, in which paramagnetic non-spherical grains are spun up by incident photons, and having been spun up, they then precess around the magnetic field direction. For our purposes, it means that if we put a spinning half wave plate between a camera, SCUPOL, and the JCMT dish, then we can recover the linear components, Stokes U and Stokes Q, and from that derive polarization direction and also polarization fraction, although I won't be talking about that in this presentation. So emission polarimetry is not a new game, and emission polarimetry on M82 isn't either. M82 was observed at 850 micron with SCUPOL, the predecessor to Pol 2, on the JCMT back in 2000 by Jane Greaves. And what they found is, I show here, a broadly elliptical magnetic field pattern away from the galactic center, which they took to be tracing what they called a magnetic superbubble driven by the superwind. However, M82 has been more recently observed by HAWC+, HAWC+ being the polarimeter on SOFIA, the airborne telescope. HAWC+ operates more in the far infrared than in the submillimetre, and observing at 53 and 154 microns, they saw really quite a different magnetic field configuration. What they see is that in the center of the galaxy, the field is perpendicular to the galactic plane. So are these two sets of observations reconcilable? We decided to have a look with Pol 2, essentially to see whether we could replicate the observations made with SCUPOL. And what we found is that qualitatively we can, which is always reassuring. When we look with Pol 2, so we're now at 850 microns, so well into the submillimetre, looking at a much colder dust component than HAWC+ sees, we still see a magnetic field in the outer galaxy that's significantly different from that in the galactic centre, and broadly perhaps concentric around the center. Whereas in the central starburst region, we see the same poloidal magnetic field that HAWC Plus sees. So how do we interpret this? The way that we interpret this is through comparison with the spiral arm morphology of the galaxy that was found back in 2005 by Mayer et al. Those spiral arms are shown on the figure here. And what we see is that while in the galactic center, the 850 micron polarized dust emission is tracing a poloidal magnetic field in the starburst, in the outer galaxy, it seems that it's tracing a spiral arm aligned or possibly toroidal field in the disk. It's at the signal to noise we're working with, it's very difficult to definitively distinguish between a spiral arm aligned and a toroidal field, but where spiral arms exist, it probably makes more sense for the field to be aligned with them than to be generically toroidal. We did have a go at quantifying this. So on these plots here, on the x-axis, we've got implied galactocentric radius. In the top panel, that's compared to the magnetic field angle. You can see there's very much two components there. One indicating the field in the central starburst up at around 170 degrees, and a more complex field associated with the spiral arms or the galactic disk. In the bottom panel, we specifically compare the spiral arm angle to the magnetic field angle for each of the vectors that we measured. And again, we can see it goes from perpendicular to the bar at small galactocentric radii through to parallel to the spiral arms at large galactocentric radii. We find that that transition occurs broadly beyond a galactocentric radius of 2 kiloparsecs, but equivalently that is 20 arc seconds above or below the bar, which for our assumed inclination of 76.9 degrees and a distance of 3.5 megaparsecs is equivalent to the transition happening at a height above the disk of around 350 parsecs. Incidentally, this isn't a new suggestion for how the magnetic field in M82 ought to work. This was predicted by Terry Jones back in 2000. This is a cartoon from his paper in which he suggested that there should be a poloidal nuclear field and a toroidal disk field. Again, this predates the discovery of spiral arms in the galaxy, but that cartoon is nicely similar to what we're observing with Pol 2 when we're looking at the cold dust component. So all of this does come together really quite nicely with the predictions. How, though, does it compare what we see with Pol 2 to what we see with HAWC Plus? So with Pol 2, we're saying that we're tracing a poloidal field to 350 parsecs above and below the plane in the starburst and a spiral arm aligned field in the disk. Whereas with HAWC Plus, the 53 micron HAWC Plus observations are very much constrained to the central starburst, but the 154 micron observations extend further out. And although we agree well in the central starburst region, it would seem that the HAWC Plus data, which is tracing a much hotter, well, somewhat hotter dust component, much nearer the peak of the SED, is tracing this poloidal geometry to significantly larger distances above and below the plane. So it would seem that while Pol 2 is seeing the disk, HAWC Plus is seeing the magnetic field in the superwind, which is interesting as first it indicates that there's a really significant amount of dust entrained in the superwind for HAWC Plus to detect. And also it allows the field lines in the superwind to be extrapolated. This is work done by Lopez Rodriguez et al. This year. And they extrapolate from the HAWC Plus data that the field lines from the M82 superwind actually connect to the intergalactic medium rather than connecting back onto the galaxy in a galactic fountain. So this suggests that the magnetization can be transferred out into the intergalactic medium, which is very interesting. But coming back to the Pol 2 data, the fact that we see this change in behavior from poloidal to toroidal at around about 350 parsecs above the plane is very consistent with models of M82, which call for the breakout from the starburst region to the superwind to occur at more or less this vertical scale height. So again, all of this nicely backs up expectations of how this galaxy should behave. So our conclusions are that putting POL2 and HAWC together, observations of the magnetic field traced by the dust in M82, we get a very self-consistent picture. POL2 is tracing the poloidal field in the starburst and a spiral armor-lined field in the galactic disk. HAWC is tracing the same field in central starburst, but then also traces the magnetic field in the superwind to show how it connects to the intergalactic medium. And I think this really does demonstrate that if we want to understand the magnetic fields in starburst galaxies, galaxies with more than one magnetic field component, we really need observations all the way across the submillimetre and the far infrared regime if we want to properly understand what's going on. And luckily for us, observations like that are now becoming available. So thank you very much for listening. And for more details, please see our paper. Thank you very much. Bye.